The problem statement from GATE Physics 2016 reads as follows. The kinetic energy of a particle of rest mass m naught is equal to its rest mass energy. Its momentum in units of m naught c, where c is the speed of light in vacuum, is. This is a numerical answer type question. We'll find our answer and then round it off to two places and fill in the blank over here. Before we start solving this problem, let's have a quick recap of some relevant concepts. This is a frame S is given. This frame is at rest. That's why you call it rest frame, or sometimes it's also referred to as the laboratory frame. And in this, we have a particle P, which is moving, let's say, in positive x direction with a speed u. And this observer, this in the rest frame, an observer is measuring this velocity to be u. Now the rest mass of this particle, we am assuming it to be m naught. Then the relativistic mass, which is given by small m, can be written as gamma times m naught, where gamma is the entity that we had seen, that it's 1 over 1 minus square root of 1 minus u square over c square. So that gamma remains the same. Note that since gamma is greater than 1, the relativistic mass slightly increase. Now once we have the mass, we know momentum is mass times velocity. So in this case, relativistic momentum would be relativistic mass versus the velocity, which is the u in this case. And if we replace m as gamma m naught, so relativistic momentum comes out to be gamma m naught u. Similarly, the rest energy, when the particle is not moving, that is, its energy is equal to m naught c square. However, when this same particle P starts to move, the energy it will have, it's called the relativistic kinetic energy, it will have a momentum component as well as the rest mass energy component. So that's it's given by this formula, square root of Pc whole square plus E naught square, and we can also write it as gamma m naught c square, where again gamma is you can see 1 minus u square over c square, and correspondingly the relativistic kinetic energy will be total energy E minus the rest energy E naught, and this is the E equal to mc square, which you have seen, I hope you would have seen, is the famous mass energy equivalence. Now that we have had a look at the relevant concepts, we'll start solving this problem by going through a series of relevant pre-checks. So first is the that we need to find all the frames used in the problem. So in the question, it talks about so there must be some frame which is observing that that kinetic energy is so and so. So there is a frame S, which we usually refer to as the rest frame, in which an observer O is observing all the motion of this particle P, right? And so there is no other frame, there is only one frame S, which we have assumed it to be rest. So we can say that S is an inertial frame, right? What about the moving frame? So there is no moving frame, so this is not applicable in this case. And finally, the number of dimensions, though the question is silent on number of dimensions, this dimensions we mean the space dimensions x, y, and z. Question is silent on that. We can simply assume to be a very straightforward 1D system, and in this case we'll assume it to be x-axis, where this is the positive x direction, right? So this is the problem that now I've reproduced that. So in the rest frame, we have a particle P, which has rest mass m naught. It's moving at some constant velocity u in the positive x direction, and we are given that kinetic energy is equal to the rest mass energy, and we're required to find the momentum. So and we know the momentum, the formula for momentum is given by P equal to m nu. So I'm writing this. So P will be equal to gamma m naught u. Now m naught is a given in the problem, but we don't know gamma and u, so there are two unknowns. But we also know that gamma is a function of u, right? So either we find gamma or we find u, and we'll be able to find the expression for the momentum P. Now we do that by solving this expression. So we know kinetic energy equal to rest mass energy. So I'm writing this expression here. Kinetic energy equal to rest mass energy is given by the term E naught. So Ke is E minus E naught, as we can see here. So I write E minus E naught equal to E naught. This gives me E equal to 2 E naught. That means total energy of the particle is twice the rest mass energy. The expression for E is written as gamma m naught c square, twice of the expression for E naught, rest mass energy, is m naught c square, m naught. So m naught c square gets cancelled. We get gamma equal to 2, right? So in the expression for P, we needed gamma, and now we can easily get the value of u if you put gamma equal to 2 here. So 2 would be 1 over 1 minus u square over c square. So this will give us 1 minus u square over c square equal to 1 by 4. This means u will be equal to root 3 by 2 into c, because it will be 1 minus 1 by 4, that will be 3 by 4, and to take the square root, so we get u equal to root 3 by 2 c. So now we have obtained the value of u as well as gamma. Now we'll put this in this expression. So we know p equal to gamma m naught u. The value of gamma we found out was 2. The value of u we found out root 3 by 2 into c. 2 and 2 gets cancelled, so we get the momentum is root 3 m naught c. So we will find the momentum in units of m naught c. So in units of m naught c, so these are the units, so the magnitude will remain only root 3. So we find that the magnitude is root 3, and so if you write, and only up to 2 decimal places, so root 3 is 1.732, only up to 2 decimal places, so we'll write our answer as 1.73. And that's all. That's why we're required to find. Thank you for listening.